Hello, everyone. My name is Jin Young Song, an associate professor at SUNY Buffalo Architecture Department. I'm very happy to be part of this fantastic event, and I would like to send many thanks to the organizers and curators of the Seoul Biennale of Architecture and Urbanism. One of the motivations of this project is based on my observation that the cities are no longer represented by permanent architectural icons. Every day and everywhere, transient and temporary events are appearing and disappearing. These are bottom-up culture of urban placemaking produced by heterogeneous desires. So I think these experiences are shared almost permanently through social media. So in my view, these temporary structures are representing the true culture of metropolis with multiplicity and diversity. So therefore, I'm interested in how the architectural fabrication method and the way of construction can respond to these dynamic urban placemaking. The action of stacking is one of the most fundamental, simple, and fun methods of parts to whole systems when you think of making a structure. So how we produce parts as products and how we assemble them into a whole implies very specific intelligence involving our culture of technology, materiality, sustainability, and socio-political agenda. Dramatic examples of this stacking method can be found in nature. Beaver's nest structured by termites, bird's nest, and so on. Their construction looks arbitrary, confusing, and scary sometimes, but energy efficient and sustainable. Materials are modified from nature, and they adjust the materials nearby. So if you compare individual animal agent to us, humans are more intelligent, but when it comes to collective practice of built environment, it is not easy to say that we are smarter than them, especially in the context of the climate crisis and the fact that building accounts for more than 40% of CO2 emissions. Therefore, multiple projects under the umbrella of instability design and the smart lab at UB mostly investigated the way we aggregate blocks. So keeping the simple action of stacking with lateral stability is the key challenge. So we studied the feature of snap interlocking to solve the problem. So many different block geometries are explored. They rely on instability of materials for the snap interlock system, and calculated control of the force equilibrium is studied through these prototypes. So block geometries here implies the system of growth and the behavior of operation. So for example, the pavilion here is fully reconfigurable. It can be packed into a standard suitcase, and also geometric freedom is also tested with a limited number of block types. For this prototype, we use the same block, but it shows the customized naked edges to pursue increased material efficiency. So phenomenon of snapping and interlocking system using that snapping phenomenon can be utilized to any scale with diverse materials. We tested wood, plastic, concrete, and terracotta. And then this slide shows the water jet cut steel. And this is the concrete blocks with the casing for reconfigurability of the stacking, and also we also utilize the harvesting novel way of green. The design stacking action can utilize 3-leg system and the 2-leg system. On the right, we use the 2-leg system using the terracotta, and then also stacking can utilize the Velcro action. So which allow the building without the actual contact, so that this can this stacking system can grow downward. So I think this is interesting and important because the simplicity of the stacking method can be integrated with machine learning and advanced robotics. So just like birds stack sticks, drones and ground robots can build and unbuild the space we need in radically different time frames. So now to present the research on this stacking, the project Step Snack would like to explore a reconfigurable construction system based on the unique stacking behavior. We learn from the traditional wood joinery method, which minimizes the bonding agents. On the left is a diagram of all sorts of the wood joineries. On the right, in Korean, is otgari chokim, which provide very stable connections between parts. So this slide shows fabrication of one unit block. So the centerpiece are 3D printed to imply a complicated geometric function necessary for the two-way snap interlock system. So legs are identical, and they cut by CNC, and it has intentional weakening in the middle of the leg for the snap interlock system into the centerpiece. The modularized 3 legs of this assembled unit block allow it to interlock with 3 other blocks. So once these unit blocks are completed, it can interlock with other 3 blocks. So that unit block can hold the weight of 1 person. And then this diagram shows that 1 block can interlock with 3 blocks. Those 3 can interlock with another 3 blocks with 120-degree rotated. And then finally, those 3 interlock with 1 top blocks. So total 8 blocks interlock each other. It becomes a rhombohedral unit cell, which is working as a one stable structural module. So this centerpiece can be improved to have minimal construction if we use the metal 3D printing from this plastic printing, so that not only it holds the identical legs, but also receive the another unit with specific pockets. And then there is a red dowels which provide the kind of shear, which provide the protection for the shear failure of the between units. So this system we tested allowed people to build variable structures, minimizing a need for skilled labor. And it also allows disassembly at the end of the program's life for use in other structural supports. A single person can conduct this transformation without tools in very short amount of time. And then the modularity of the system can also utilize the integration with the skin units. So these prototypes were tested at the Smart Lab at my University of Buffalo and Smart Lab. And then this is the photo last week at the Seoul Biennale at DDP second floor. And then I appreciate the support from all the positive comment and a lot of help from curators and also the staff from UCIAG for the entire research and the installation process. So this prototype presentation and this research at the Biennale aims to demonstrate the reconfigurability of the stacking system, and then I hope that this will be developing to the next level to present it as a mode of broad sustainability of our built environment. Thank you very much for listening.